Next, we will discuss the concept of implicit differentiation that allows us to differentiate any function regardless of whether it is given explicitly or implicitly. First, let's recall the table of basic derivatives and let's practice applying the linearity rule for linear combinations of functions, one of which is known and one isn't. We will label the unknown function with the letter y. By the linearity rule, we pass the differentiation through addition of functions and factor out the constant coefficients to get the following result. Now we can replace the derivative of x cubed with its actual derivative, but since y represents an unknown function, we would have to keep writing its derivative as y prime. We got the derivative. Of course, we can further simplify it, but that's not the point of the exercise. Here's another example. Applying the linearity rule and plugging in the derivatives where we know them gives us the following result. Now, let's practice applying the product rule for products of functions, one of which is known and the other one isn't. We will label the unknown function with the letter y. By the product rule, we get the following result. Now, we can replace the derivative of x squared with its actual derivative, but since y represents an unknown function, we would have to keep writing its derivative as y prime. Here's another example. Applying the product rule and plugging in the derivatives where we know them gives us the following result. Now let's do the quotient rule. And let's find the derivatives of quotient of functions, one of which is known and the other one isn't. We will label the unknown function again with the letter y. By the quotient rule, we get the following result. Now, we can replace the derivative of x squared with its actual derivative, but since y represents an unknown function, we would have to keep writing its derivative as y prime. Here is another example. Applying the quotient rule, plug in the derivatives where we know them, and we got the derivative. Finally, let's practice applying the chain rule for compositions of functions, one of which is known and the other one isn't. We will label the unknown function with the letter y. By the chain rule, the derivative of the composition is the derivative of the outer function multiplied by the derivative of the inner function, so we get the following results. As a matter of fact, in many tables of derivatives, this is how the derivatives are presented. Note that the derivative of the outer function is found in terms of y, which is unknown, but once it becomes known, we can replace y and y prime with the appropriate expression. Now we can put it all together and introduce the idea of implicit differentiation, which is actually quite simple. Basically, the idea is that if two functions are the same, then their derivatives must be the same. So let's differentiate the both sides of the definition of our function. Now, using the linearity rule on the left side and the chain rule on the right side, we obtain the following result. Here, you should be able to recognize that we already found all the needed derivatives in the earlier slides, so we can now simply plug that in to get the answer. Of course, since the function was given to us implicitly, the derivative, the way we found it, is also in implicit form. We can simplify it further, but the task of implicit differentiation ends here. To simplify, we expand the expressions on both sides, collect all the y primes on one side, and then combine the like terms and isolate the y prime. But keep in mind that this is not calculus but just simple algebraic manipulations. The task of implicit differentiation ended in the previous slide. Similarly, we can now find the derivatives of many functions such as this one, by first raising both sides to the third power, and then taking the derivative of both sides, and plugging in the derivative where we know it and leaving it alone where we don't know it. And then isolating the y prime gives us the following result. We can generalize the same approach for any index n by first raising both sides to the nth power, and then taking the derivative of both sides, plugging in the derivative where we know it and leaving it alone where we don't know it, and isolating the y prime would give us the following result. We discussed the process of finding the derivative of a function given implicitly, called the implicit differentiation process.